Welcome to Causal.
Picture a blistering hot day in July. Across town, people are lining up at ice cream trucks, and at the exact same time, people are heading out to the local pools and beaches. Now, if we plot the local statistics on this split-screen line graph, we see a striking pattern. As the sales of ice cream go up, the number of drownings in the area rise at the exact same rate. The math is clear. The two numbers are moving together. So if you want to save lives, should you immediately ban all ice cream sales? Of course not. That leads us to the most important rule of working with data. Just because two things move together, a correlation, does not mean one is actually making the other happen. To understand what's happening, look for what we missed. Extreme summer heat drives people to buy cold treats and into the water. We call this hidden variable a confounder. It creates the illusion of a direct link where none exists. While the ice cream example is an obvious coincidence, the same logic applies to any business. Trusting a correlation without looking for the confounder leads to decisions that are confident, expensive, and ultimately wrong. The business world is filled with overlapping data points that mimic this ice cream illusion. Sales, clicks, and loyalty metrics are constantly rising and falling together. When you want to prove for certain that one action causes a specific result, the gold standard is running a randomized experiment, or A/B test. But in the real world, you can't always run a clean test. Sometimes it's too expensive, or you're looking at historical data where you can't go back and change the past. When testing isn't an option, we use causal inference. It's a systematic way to deduce true cause and effect, strictly by looking at the data we already have. Without a framework to interrogate this data, organizations are left guessing whether their actions actually caused their success. To practice causal inference, you first have to take your assumptions about how your business works and make them visible. We use a DAG, or Directed Acyclic Graph. Blank circles represent variables. One-way arrows show what causes what, making assumptions visible. Mapping forces us to spot potential confounders. Adding a hidden factor often shows it actually drives the flow. Once that confounder is on the map, we can use math to account for its influence. We effectively isolate its effect so we can see the real link between the variables we care about. This process keeps teams from claiming certainty when they might be missing the key factors that actually matter. Let's look at a music app called Stride. They notice that users who try a new playlist feature renew their subscriptions at a much higher rate. The correlation is huge. Playlist users renew at double the rate of everyone else. It's tempting to credit the feature for the loyalty and pour the entire marketing budget into promoting it. But the team uses a DAG to pause. They ask, is the feature actually causing the loyalty, or are naturally loyal users simply more likely to try out new features? They spot a confounder, user engagement. Highly engaged users log in every day, finding the new tool, and we're never going to cancel anyway. By mapping the logic, the team realizes that engagement was driving both actions, revealing that the double renewal rate was largely a coincidence. To get the truth, they adjust their analysis. They compare users who have the exact same level of initial engagement to see if the feature still makes a difference. The adjusted result shows the feature's effect is real, but smaller than it first appeared. Because they saw the true effect, Stride promotes the feature, but doesn't overspend based on the original inflated numbers. Now, if a simple A/B test is possible, you should just run it. And if you only care about making a prediction, the why might not matter as much. But when you need to know if one thing really causes another, causal inference is your shield against coincidence. It's how you turn data into honest strategy.